invited to the evening session. So we'll have 3 talks. And the first talk is by Pavel Etingof from MIT. Please, Pavel, the floor is yours.
Okay, thank you very much. Yeah, okay, so I want to start with the fact that this talk is at a very difficult time. We are witnessing a horrible invasion of Ukraine by Putin's troops, and I stand with the Ukrainian people, Ukrainian mathematicians at this time. I grew up in Kiev, in west suburbs of Kiev, where there is heavy fighting right now, and I went to mathematical school number 145 in Kiev, and then Kiev University for 2 years. And so my thoughts are with people in the Ukraine, and also with people in Russia who are against the war and who are being persecuted, because situation in Russia is, you know, is getting worse by the hour in terms of the oppression there. And so my thoughts are with mathematicians of both countries and people of both countries who are fighting against this invasion. Okay, and so let me now share my slides. Okay, so I share my screen. Let's see. Okay, can you see my screen now?
Yes, we can see the page. Yes.
Okay. So, so I will talk about my joint work with David Kazhdan and Edward Frankel about analytic Langlands correspondence and Hecke operators. So this is an extension of Langlands correspondence to so ordinary Langlands correspondence for fields of rational functions on a curve is well, it happens over a finite field, and what we do is an extension of this to local field, which includes in particular Archimedean fields, real and complex numbers, as well as non-Archimedean fields. And in the Archimedean case, which I will mostly focus on, this is related to all kinds of integrable systems, because many integrable systems are encompassed by a kind of big umbrella, which is quantum Hitchin system. And so these systems appear in this story. It is also a kind of analytic extension of the geometric Langlands correspondence. So geometric Langlands correspondence deals with D modules on the moduli space of bundles. D modules are come from differential equations, and this story is more about solutions of these differential equations. So let me start with some definitions. So, so for me, X is going to be a smooth projective curve over complex numbers, which is the same thing as a closed Riemann surface. The genus will be G. And so then I will also want to consider points on it, T1 through Tn, distinct marked points. And then we will consider the space, moduli space of stable parabolic, or rather more precisely, quasi-parabolic PGL2 bundles of degree m on X. So what is a PGL2 bundle? PGL2 bundle is a rank 2 vector bundle, which is the same thing as a GL2 bundle, modular tensoring with line bundles. So this is actually a smooth complex variety of dimension 3g minus 3 plus n. So let me explain what does it mean that we consider stable. So these are holomorphic bundles, but we only want to consider stable bundles. Let me explain what this means. So so let's consider a rank 2 vector bundle, so 2-dimensional vector bundle. So classically, the slope of this bundle is degree divided by rank, so 1/2 of the degree. But in the case of parabolic bundles, so first of all, let me explain what is parabolic bundle. Parabolic bundle just means a bundle such that at every point T1, T2 up to Tn, we fix a line in the fiber of the bundle. So this is a 2-dimensional bundle. So we have a 2 plane sitting at every point of X, and then we just fix a line in this plane through the origin. So it's a point of projective line, projectivization of this fiber. So this is what it means to have a parabolic bundle. And then there is a notion of stability, which is the following. So we have the classical notion of slope, like I said, it's a 1/2 of the degree, but then we add to it 1/4 of the number of points. And then if you have a line subbundle in E, well, again, classically, its slope is just the degree, but we add NL over 2, where NL is the following number. So this actually depends on these parabolic structures. So, so if you have a line subbundle, this means that in every fiber you have a line. And then let us look at the fibers over those parabolic points, T1, T2, T3, and so on. So we have the line coming from this line subbundle, and we also have the parabolic line. And so if they coincide, we will say that this parabolic line is contained in the subbundle, and the number NL between 0 and n is the number of parabolic lines contained in the subbundle. This bundle E is called stable if the slope of every line subbundle of E is less than the slope of E. So this generic bundle will be stable, and stable bundles form a smooth variety. Also this degree M, well, because we are working modular tensoring with line bundles, when we tensor with a line bundle of degree D, M is replaced by M plus 2D, and therefore we only have 2 degrees to distinguish, 0 and 1. And so, so therefore we have this manifold is a union of 2 components. And what we will consider, so we want to do harmonic analysis on this space. And then, so we will consider for the harmonic analysis, we need some Hilbert space, and we will define HI to be L2 of this ban I stable of X. So what do I mean by L2? So normally, well, I mean, if we consider the L2 functions, we would need a measure on this manifold. We don't have a natural one. So the way out is, instead of considering functions, we should consider half densities. So we are considering square integrable half densities. So if you have a half density F, then absolute value of F squared is naturally a density which can be naturally integrated over X. So this kind of space we can define without fixing any measure on, without fixing any measure on this ban X. And so H is the sum of the 2 Hilbert spaces, H0 and H1. And so we will do harmonic analysis, which will mean that we will consider some operators in these spaces, and we'll look for Eigen functions of those operators. So this is a kind of crucial difference with ordinary Langlands and also with geometric Langlands, is that in both of those, we consider the entire stack of G bundles, not just stable bundles, but arbitrarily degenerate bundles as well. And that's important. So for example, in the case of ordinary Langlands program, automorphic forms are functions on the set of all bundles, which is a discrete set. But if you throw away unstable bundles, you will lose much of the information. And here we're consider stable bundles because they kind of, the rest is kind of set of measure zero. So if you consider L2 space, you do not care. Okay, so now so the kind of main objects in the theory of automorphic forms in the usual Langlands story is Hecke operators. So Hecke operators act on functions on the space of bundles, and their Eigen functions are automorphic forms. And so we want to define Hecke operators also here. And so let me explain how to do this. So for this, we need to define the notion of Hecke modification. So Hecke modification is an operation which is applied to a bundle E, GL2 bundle E, parabolic, at a point X of our Riemann surface or curve, which is different from any of the parabolic points TJ. And so the way it's done is the following. So if you have a bundle E, then to do a Hecke modification, you need to fix a point X and also S, which is a line in the fiber of E at this point. And then you can define a new bundle, which is called HXS of E. And the easiest way to do it is to say what are holomorphic sections of this bundle. So holomorphic sections of this bundle are meromorphic sections of E, which are holomorphic outside of X and have at most first order pole at X, and residue at this pole must be in S. Of course, residue is not well defined. To talk about residue, we need to choose a local coordinate, but residue up to scaling is well defined, and that's all we need to say that the residue is in S. So if you start with a stable bundle, then this resulting bundle is not necessarily stable, but generically it is. So for generic values of parameters, it is. And so then we define Hecke operator, which is an operator on this Hilbert space, in which is defined, well, first the rough definition in the following way. If I have a function psi of on this space of bundles, then Hecke operator. So Hecke operator is operator depending on a point on the curve X. So it's HX. So HX psi acting, this psi is a half density of on the space of bundles, and so HX psi is another half density. So to compute it at point E, the answer is that it is we should take kind of averaging of psi over all Hecke modifications of E, where the point X is fixed, but S varies over the projective line, over the line of all projective line of all the lines in this fiber, and with respect to some measure ds. And well, so this is not the real definition, because first of all, there is an algebraic geometry's question, which is what is this ds? There are many different measures, so which one do you take? And also analyst's question, even if I answer that question, why does this integral converge? For which psi does it converge? So it will turn out that it converges for some dense subspace of psi's. And in what sense does it define an operator? So it's a densely defined operator. To what extent does it really extend to a bounded operator, for example, from H to H? And in fact, so the first question can be answered, but the second question, an analytic question, is more difficult. And actually, in general, the answer is conjectural, and only in genus 0 we have a complete story. So let me now stop for questions.
So there could be more than one measure, right? Or in the end of the day, you say there will be only some
No. There is a natural. So there is a natural measure to put here. There is a natural measure that comes from some story about affine Grassmannian. But then there is an analytic question of in what sense this defines an operator, and that question is not so simple.
Okay.
Other questions? Okay. So when I say one can show that this makes sense canonically, it means that there is a certain natural measure. I don't have time to explain this, but this is some piece of algebraic geometry. It's not too difficult. And this is due to Beilinson. This part is due to Beilinson and Drinfeld. So this is so we work over so we work over complex numbers. So when I write norm of ds, this means ds times ds bar. Okay, and so the first conjecture is, so this is a densely defined operator. So if psi is a sufficiently nice function, for example, it is compactly supported inside the space of so-called very stable bundles, then you can, the integral converges and you do end up, so you do obtain a function, and then you conjecture that it lies in H, and moreover, it extends to a bounded operator. So these operators are, and in fact, we conjecture that they are compact, self-adjoint, and pairwise commuting. Well, real conjecture is that they're compact, because once that's known, it automatically follows that they are self-adjoint and also that they are pairwise commuting, because Hecke modifications at different points are done independently.
Sorry, just one more question. So this is sort of the analytic version, but is there a holomorphic version of this? So you instead kind of doubling things, or is it on L? So since ds is ds.
Yes. So the holomorphic version is in some sense geometric Langlands. So this can be thought of as, okay, so in conformal field theory, for example, we have
you will have a holomorphic block and a conformal block, and it's conjugate, right? So you will have a,
that's right. So having only holomorphic, so in conformal field theory, we can talk about conformal blocks, and then we can talk about pairing conformal holomorphic and anti-holomorphic blocks. And similarly here, so if you only talk about holomorphic things, this will be a story about quantum Hitchin system. I will get to that in a second. But then when you pair holomorphic and anti-holomorphic, this is exactly what you get. And in some sense, this can be made more precise. So actually, this appeared in some works of Teschner. And the idea is the following, that you can consider Vesumina-Witten conformal field theory, but a non-compact version when you consider it for non-compact Lie groups, such as SL2C instead of SU2. And then if you do it at critical level, this is the kind of theory you will get. Does it answer you?
Yeah, sure. And also the question in chat, which is, I guess you also answered, can we write the holomorphic version of Hecke operator in this integral form? I guess the answer is yes, it's the conformal block, right?
No, no, there is no Hecke operator. I don't think we have a holomorphic version of Hecke operator, but we have definitely holomorphic version for Eigen Functions of Hecke operator. So Eigen Functions are going to be obtained from Eigen Functions of quantum Hitchin system, which are purely holomorphic, but they're not single value.
That makes sense. Yeah, thank you.
All right, so let me say, so this operator is compact, self-adjoint, pairwise commuting, and here is, well, one suppose, so I will assume this conjecture, we can prove it in genus 0, and in some cases in higher genus, very few cases actually, and so once we know this, then there is a theorem that these operators commute with so-called quantum Hitchin Hamiltonians. on this bond space and their conjugates. So I will explain what are quantum Hitchin Hamiltonians. So what is that? So recall that usual Hitchin system. So we have usual Hitchin system is an integrable system on the cotangent bundle of the moduli space of bundles, and the point in this space is a pair bundle and the cotangent vector phi, and cotangent vector phi is simply a one form on X with values in endomorphisms of this bundle. Then there is the integrable system is a Lagrangian fibration which maps this thing to B, which is a affine, which is a vector space called the Hitchin base, and it is H0 of X with coefficients in the square of the canonical bundle. This is a vector space of dimension 3G minus 3 by Riemann-Roch theorem. And the map from here to here looks as follows. We attach to E comma phi just the trace of phi squared. So the trace of phi squared is so phi is a one form, so a trace of phi squared will be a quadratic differential, and that's an element of this space. This is a very rich family of integrable systems, which can be extended to arbitrary groups, Lie groups. This is for PGL2, and also you can consider wild ramification. And then it's a very rich family, such that many finite dimensional integrable systems are special cases of it. And Drinfeld and Berenson and Drinfeld discovered a way to quantize this system. So the quantization of this system is a commutative algebra of differential operators on BAN, critically twisted. So it's twisted by the critical bundle, which is a square root of the canonical bundle. So associated graded of this commutative algebra is this algebra of functions on B. So you can think algebraically, you can think about this integrable system as a map from polynomial functions on B to functions on the cotangent bundle. And this map gets lifted to a map like this, except that this space B tilde is no longer has a natural origin. It's an affine space whose underlying linear space is B, and this is a so-called space of operas. So this is something that will show up a bit later. And the way this is done is roughly as follows. So G is PGL2 here, and so recall that this moduli space of bundles can be thought of as a double quotient of a loop group G of T by the Taylor series subgroup, and on the other side by functions on X minus 1 point here. So we have a point here, and we can fix a local coordinate in this point. Then any rational functions on X minus this point with values in the group can be expanded in a Laurent series, and so this sits inside here, and this double quotient is exactly 1, because what this double quotient tells us is so we can have two charts. One chart is the curve without the point, the other chart is a little disk around this point, and bundle trivializes on both charts. And then to glue, we need to clutching function, which lies in here, and it is defined up to left multiplication by this subgroup and right multiplication by this subgroup. And then, yes?
What do you say for the monodromies of the operas at the mark points here?
Well, right now I'm explaining without marked points, but if you have marked points, monodromies will be unipotent. in the simplest case.
Thanks.
Okay, so and the way the system is constructed is the following. So we have, so let's consider two-sided invariant differential operators on this group. So those come from central elements of universal enveloping algebra, or maybe some completion. And we do have such elements at critical level. They are the Sugawara elements, which at non-critical level define action of Virasoro, but at critical level, they just give central elements. So they give rise to two-sided invariant differential operators on this group. And then those operators descend to commuting differential operators of second order on the double quotient. Well, they of course become dependent, but there are, we can pick 3G minus 3 independent ones among them, and they will give you this Hitchin system. Okay, and so this is what Hitchin system is. And so the theorem is that these operators commute, Hecke operators commute with the quantum Hitchin operators and their complex conjugate. And then we can do harmonic analysis. So we have compact self-adjoint operators. So by the standard theorem in functional analysis, they have a basis of Eigen functions, discrete, labeled by some discrete set, psi lambda, labeled by some lambdas, and the Eigen functions of Hecke operators, and eigenvalue is some function beta lambda of x of a point on the curve. And in fact, it turns out that naturally this function is not a function, but a -1/2 density. And we might ask, what are these eigenvalues? And it turns out that they are that they are solutions for the Oper differential equation. So, so what are Opers? So I already said that Opers are points in the spectrum of this quantum Hitchin algebra, but more explicitly, Opers for PGL2 are for SL2. Actually, Opers are for the Langlands dual group, so they are for SL2. They are differential operators from k to the -1/2 to k to the 3/2, where k is the canonical bundle of the curve x. And they're required to have symbol d squared, which means, well, so this, because this is a map from k to the -1/2 to k to the 3/2, it is well defined to say that the symbol is d squared, independent on coordinates. And also they should be formally self-adjoint, which means that in local coordinates, they look like d squared plus u, a Hill operator or Schrödinger operator. They don't have a middle term. And so Oper is any such operator. And Opers form an affine space whose underlying vector space is quadratic differentials, because this u is naturally a quadratic differential. Or at least, well, u is not, but if you replace, I mean, if you replace u by u plus v, then v is naturally a quadratic differential. But the condition for Opers that appear in this business is there is a condition on their monodromy. And the condition is that monodromy should be in SL2R. So, as I said, Opers, so if there is no marked points, this is it. And if there are marked points, then Opers should have logarithmic singularities with unipotent monodromy at the marked point. So monodromy is supposed to be in SL2 or equivalently SU11. And then this function beta lambda of x. So it turns out that there is the set of Opers satisfying this condition that they have monodromy in SL2 is exactly, it's a discrete set. So in fact, in the space of connections, we have two Lagrangian subspaces. one is space of opers. This is a holomorphic Lagrangian. And then the other is the space of connections with real monodromy. And it turns out that those two Lagrangians intersect transversally, but they're transcendental. So the intersection is a discrete but infinite set. And that's exactly the spectrum of those self-adjoint operators. And so this can be thought of as follows. So we have these differential equations, and they are second order. So they have two solutions up to linear transformations, F1 and F2. And moreover, there is an invariant indefinite Hermitian form on these solutions, which is invariant under monodromy, because monodromy is an SU11. And so, so therefore, we have a real solution, beta, which is F1, F2 bar plus F2, F1 bar, and F1, and this solution is single valued. And then it satisfies this system of equations. So the eigenvalues of Hecke operators are exactly obtained like this. Hecke operators eigenvalues are labeled by these real opers, and once you fix a real oper, the corresponding eigenvalue is obtained by this procedure. And I will explain how this is connected to quantum Hitchin system in a second. But before this, I want to see if there are any questions. And then I will explain, I will finish this part, and I will explain much more explicitly how these things look like in genus zero. Okay, so so we'll discuss that there is this quantum Hitchin algebra, and its spectrum is the space of opers, which I call B tilde. So this means that if I have an oper, this gives a rise to a character of this algebra. And the theorem is that so remember that eigenfunctions of Hecke operators are labeled by real opers and L lambda. And the theorem is that they are also eigenfunctions of quantum Hitchin operators. And eigenvalue is exactly the value of this character on D. So D psi lambda is chi psi lambda, and D bar psi lambda is chi bar times psi lambda. And so we have a conjecture that the spectrum is simple and it is labeled by all real opers. And these conjectures are essentially proved in genus zero and in a small number of cases in higher genus. Okay, I should also mention that the problem makes sense over other local fields, in particular real numbers. And for real numbers, it's related to all kinds of interesting geometry, cluster varieties, and so on. Also, I want to mention some references. So Hecke operators appeared in the work of Braverman and Kashdan in 2006. Hecke operators for local fields, Kontsevich paper in 2007 on motives and positive characteristics. Then Langlands wrote an article in Russian where he proposed that geometric Langlands should be made more analytic in the sense that one should consider functions, not only D modules. And then Teschner wrote a paper in 2017 where he proposed this idea of real opers appearing in the corresponding problem for single-valued eigenfunctions of the Hitchin operators. And then there were work of physicists, there was work of Nekrasov and collaborators, Kapustin, Witten, Shatashvili, others. Then there was a recent work of Gayota and Witten already after our work, where they made physical sense of what we did. And I should mention that for the simplest interesting example, for P1 with 4 points, Bakers in 2007 wrote a paper where he talked about this kind of spectral problem. Okay, so I think I will now switch to more explicit examples. So any questions so far? Okay, so now I'm going to consider just the case of P1, x equals to P1 with 4 points. And so then, so we have 4 points, 0, 1, t, and infinity, where t is in our field. So it works over any local field, but you can think of t being in field being complex field. So that now I have to fix parabolic structures. So I claim that this bun 0 s is just P1 without 4 points. The same 4 points, namely given, so the bundles, degree 0 bundles that are stable, they are all trivial, O plus O. And then a parabolic structure is determined by fixing a line in the plane. So this can be done by fixing a point on P1. And we will fix, and so we have to fix 4 points in P1. But this is all modular GL2. So all that matters is the cross ratio of those 4 points. And let me call it Y. So this means that at the point 0, at the point x, at the point 0 of P1, the parabolic structure is 0. At the point 1, it is 1. At the point infinity, it's infinity. This pins down the symmetry under PGL2. But then at the point t, it is going to be y. And so this bundle, parabolic bundle, is denoted by EY. And it turns out that it is stable if and only if y is different from those points. So this bond space is just a one-dimensional space with coordinate y. And so now we can identify also bond 0 and bond 1 by doing Hecke modification at infinity using the parabolic line. And so now we can write the Hecke modification explicitly. So Hecke modification of the bundle EY will be bundle EZ for some Z. Okay, this is a bundle of degree 1, but I identified with degree 0 using this, and then it will be EZ. And then there's, you can compute, it's a nice exercise that Z is given by this formula. S minus 1 times ST minus XY over S minus X times S minus 1. And then we can write down a formula for Hecke operator. It's a bit more convenient to write one, you multiply it by this factor, normalization factor. So H is the space of square integrable half densities, but by using dx to the 1/2, we can reduce it to just ordinary L2 functions. And then the Hecke operator is given by the following formula. Hx psi of y is the integration over our field. So if you like complex numbers, psi of this Hecke modification times this measure, which I said was natural. And you can compute it in this case, and it is ds divided by s minus x times s minus y, norm of this, which means that this differential times its complex conjugate for the complex field. And we can compute this operator a little bit more explicitly. Namely, we can, well, I mean, usually integral operator is written as h psi of y is equal to the integral of some kernel k of yz times psi of z dz. And this is not in that form. So for that to be in that form, we need to put, we need to make a change of variable where this expression becomes a new variable z. So that's the change of variable we make. So instead of s, we use the z. However, this is a quadratic map. This is a degree 2 map. It's a double cover. And this means that when we make a change of variable, we will get a factor of 2, and also integration over complex numbers. That's the only change. And for the real numbers or other local fields, the change will be that we will integrate only over the image of this double cover. So double covers are surjective over algebraically closed field, but over non-closed field, they may not be. And so we will integrate only over the image. And here is the final answer. Which can be found also in Kontsevich's paper in 2007. So we have this remarkable polynomial ft of xyz, which is this polynomial xy plus xz plus yz minus t squared plus 4 1 plus t minus x minus y minus z times xyz. And then this operator, its kernel, is basically the following. It's so this theta is really, it's an indicator whether this expression under theta is a square or not. So for complex numbers, this is just 1. And so this is just 2, which is our factor of 2, integration of psi divided by the square root of this polynomial. So this is a perfectly explicit formula. And moreover, we see that this integral converges. So it's more precisely the way, so this polynomial in the denominator is quadratic with respect to each variable. And so if I fix all variables except 1, it's a quadratic polynomial. So if it has distinct roots, then integral will converge because it will have 2 square root singularities near each of those roots. But if the roots coincide, then there will be a logarithmic divergence. So here is this corresponding integral. And so this means that if I apply it to, say, a smooth function, the result will be a function that has logarithmic singularities. And it will have logarithmic singularities exactly at those 4 points, 0, 1, t, and infinity. And then you can prove that this operator is compact and self-adjoint just by using this explicit formula. You can estimate. So for complex numbers, it is just this. And so you can check, the way you can check it's compact is, okay, so the easiest way to check that some operator is compact is to check that it is Hilbert-Schmidt, which means that its square has finite trace. Because that condition is very easy to write down in terms of the Schwarz kernel. It just means that Schwarz kernel must be in L2. Well, unfortunately, this doesn't hold in this case because this Schwarz kernel is this integral of Schwarz kernel square logarithmically diverges. So what is true is, well, hx to the 4th turns out to be trace class. So hx squared is Hilbert-Schmidt. And in fact, hx to the power 2 plus epsilon already is trace class. But epsilon has to be greater than 0. Another thing you can do is compute asymptotics of this operator hx at for example, at x goes to infinity. And what happens is it turns out that it becomes a scalar in the limit, except that there is a factor in front of the scalar, which is log x over x. So it has, okay, so if you really rescale it to be if you write it as a minus one half densities, which is what it's supposed to be, it has a logarithmic singularity at x equals to infinity. And then we have a spectral decomposition. So if you take operator hx and apply it to psi n, you get eigenvalue times psi n. And so we can choose those eigenfunctions to be real and positive near infinity, and that fixes the, and also normalized, we want them to be have L2 norm 1. So then they are uniquely determined, and it is, one can show that they are smooth outside those points and have logarithmic singularities at those points. And now, one interesting thing about this 4-point case is that the kernel of this operator is actually symmetric, not just, okay, the self-adjointness means that it's symmetric under permutation of y and z, but it actually is also symmetric with respect to permutation of x and z. It is in fact symmetric in all three variables, x, y, and z. And this is a very special case of this, this is a special feature of this 4-point case, and it has a lot to do with Painlev 6 and with Okamoto symmetry for those equations.
So I guess the construction for a torus with a puncture should be similar, right? Because it's accidental.
Absolutely, yeah. If you have a torus with a puncture, you will get more or less exactly the same story with one puncture.
With one.
Yeah, one puncture. Yeah. Okay, and so and for this reason, the eigenvalues beta n are more or less the same as the eigenfunctions. They differ by a constant, and therefore we have this reproducing kernel formula. So this is a sum over Cn times Cn of x, psi of y, psi of z, and then you can see that this Cn is just the reciprocal of the asymptotics of this psi n at infinity, which means, okay, so psi n has a logarithmic singularity. You normalize psi n by having norm L2 norm 1 and positive, and it is positive near infinity. So it looks like log multiplied by some constant Cn to the -1, and so Cn is just the reciprocal of that, and so so therefore the full final formula for this reproducing kernel is that this is the sum of psi n of x, psi n of y, psi n of z divided by psi n infinity. So skip, this is not very important, but so let me now note what happens in the so for Archimedean field, we also have these quantum Hitchin operators which commute with our integral operators. And in the case of 4 points, this is nothing but the so-called Lamé operator. Well, or more precisely, it's related to the standard Lamé operator by the so-called Halphen transform. And it is the Lamé, so the Lamé operator, so if you related to the torus with one puncture, elliptic curve, you will get operator du squared plus 1/4 of the p function. So normally you have du squared minus m times m plus 1 times the p function, and this means that the coupling constant m is equal to -1/2 for this particular. I should say that there is a twisted version, so you can twist the theory at every parabolic point. And in this case, you will get, you can get arbitrary m, and in fact, you can get the so-called Darbu equation, which has poles at all points of order 2 with arbitrary coupling constants. So p functions with arbitrary coupling. But in this case, so the fact that the integral operator commutes with this L, expressed by this differential equation that applying L with respect to y to the function 1 over square root of f t of x, y, z is the same thing as applied with respect to z. And so therefore we get that eigenfunctions are Lamé functions. Well, except that they are not holomorphic Lamé functions. They are real analytic functions, which are combinations of holomorphic and anti-holomorphic ones. So they satisfy this equation L psi n equals to lambda n psi n, where lambda n are some values of this accessory parameter, and also complex conjugate equations. So for complex numbers, this psi n looks like this: f1n of x times f2n of x bar plus f2n of x times f1n of x bar, where these are a basis of solutions of the Lamé equation. And these lambda n's are accessory parameters for which monodromy of Lamé equation is real. And this was studied by Beukers in his paper 15 years ago. So if you take these eigenvalues and take square root of them, you will see something like lattice of periods of our elliptic curve, but it will be distorted. So at infinity, it will look like lattice, but in the finite region, it will be distorted. And this is single valued. So because monodromy is real, it lands in the group SL2R, which is the same as SU11. And so this combination is going to be single valued. And also the monodromy matrices at 4 parabolic points are unipotent. So, okay, so we have this indefinite form, which is invariant. And the proposition is that eigenfunctions of Hecke operators correspond to points lambda and c, such that the monodromy of the Lamé equation is in SL2R. And there is a discrete set of such eigenvalues. Maybe I should mention that there is the largest. So this Hx is an operator. So the kernel, Schwarz kernel of this operator is positive. It is the 1 divided by square root of the norm of something. So you should think of it as an infinite matrix with positive elements. Such a matrix has always, by Frobenius-Perron theorem, has the largest positive eigenvalues, such that the corresponding eigenvector has positive coordinates. In function analysis setting, this means that there is a largest positive eigenvalue, such that the eigenfunction is everywhere positive. And this is exactly what is related to analytic uniformization of the Riemann surface CP1 without 0, 1, t, and infinity. So this means that it really computes the Poincaré metric on this surface. So other eigenvalues correspond to other real projective structures. These projective structures are obtained from this one by so-called grafting, which was introduced by Goldman. And also these structures were studied by Faltings, who proved that they form a discrete set. And they exactly arise as the spectrum of operators, Hecke operators in this story. So let me just explain this example with analytic uniformization very quickly, because it will be clarifying. I'm borrowing this discussion. This is classical, goes back to 19th century, but I borrowed discussion from Takhtajan's paper. So this is a Riemann surface, which is hyperbolic. So therefore it has universal cover, which is upper half plane. And we have a covering map called the J. This is the analytic uniformization map. So we can invert this map and we'll get a multi-valued map from this Riemann surface to C+. So it's a multi-valued holomorphic function. And then we can define two other functions. Psi1 is 1 divided by the square root of J inverse prime, and psi2 is I times J inverse divided by the square root of J inverse prime. And then it turns out that these psi1 and psi2, which are also functions, multivalued holomorphic functions, they form a basis of solutions of the Lamé equation, L psi equals to lambda 0 psi, where lambda 0 is the accessory parameter corresponding to this uniformization story. And therefore, you can form these functions. So in particular, it has, so we can form this Hermitian combination, psi1 times psi2 bar plus psi2 times psi1 bar. And this is twice the imaginary part of J inverse of Z divided by J inverse prime, absolute value. And this is, note that this is positive because J inverse takes values in the upper half plane. And so imaginary part of J inverse is positive. And this function also satisfies a system of differential equations like this with positive beta. And this beta is exactly this Frobenius-Perron eigenvalue, so it's positive. And this beta, recall that this is a minus 1/2 density. So beta to the -2 is an ordinary density. And it is exactly the conformal metric. So recall that the conformal metric is the same thing as a density. And so it is the conformal metric of the Poincaré conformal metric. So it has curvature -1. And that's how you compute that that curvature, that metric. So any questions up to this point? All right, and so maybe let me just finish by explaining what happens in higher number of points. So in this case, we have bundle. So again, we have trivial bundle O plus O, and parabolic structure are the following. So we have points, and let us say the points are 0, t0 equals 0, t1 through tm, and then tm plus 1 equal to infinity. So then parabolic structures are 1. We can always make sure that they're 1, 0 at 0, 0, 1 at infinity, and 1, y1, 1, ym at the points t1 through tm. And then this is defined up to symmetry. Y1 through ym can be multiplied by a scalar. So this means that we have a birational model for this space of bundles by projective space Pm-1, which is the space of vectors like that, modulo dilations. And then you can compute again Hecke modification. So it's going to be given by this formula. And then Hilbert space H is going to be the space of half densities on projective space, which is the same thing as functions on the vector space of dimension m of homogeneity degree minus m over 2. So they satisfy this condition. So this is you can also think of them as functions on f m plus 1, which are translation invariant and homogeneous of degree minus m over 2. And then you can write down this Hecke operator, and it has this form. So there is this explicit formula, and we proved that it is bounded and compact, and then its eigenfunctions are also eigenfunctions of the Godin system. But I think I should stop.
Yeah, so we're going, yeah, a little bit over time. In fact, yeah, I was about to ask a question. So you're saying there's a Godin system and then there's a beta ansatz, right? So this the spectrum, right, of the Lamé operators can be also found by beta ansatz, in this case from Godin model. Is that right?
Okay, not quite, because this is a Godin model not on finite dimensional spaces, but on infinite dimensional. So
there's no construction there, or
no. There is no beta ansatz in that case, but there is a version of this story where beta ansatz will appear. So if you consider it not over a complex field but over a real field, then it turns out if over real field you have to fix a real form of your group at every point. So real curve. So if you have an algebraic curve over real field, then it has a real locus, and real locus is a bunch of ovals. And then it turns out that on each oval you need to fix. So for example, if you have P1, the simplest case is when the oval is just the real RP, and then you have to fix a real form of your Lie group. So in particular, so you can fix the compact Lie group SU2, and in that case, what you get is you get the usual Godin model for tensor product of finite dimensional SU2 modules. And then indeed your Hilbert space will be finite dimensional in this case, and the solutions will be exactly the usual Godin eigen vectors.
I see. And then sort of on the level and then on the level
and then beta ansatz will apply. Yes.
And then is there some truncation condition you can impose in those integrals so that would happen, right? So that would sort of truncate the which would enable what you just described. So we have finite. So it's just specifying the weights of these representations,
yes. So there is some. Okay. So there is a first of all, well, if you want it to work in the setting of functional analysis, you need unitary representations. And so in that case, somehow these finite dimensional representations of SU2 are isolated, so you can't represent it that way. But if from algebraic point of view, yes, there is a family, and at some points these finite dimensional representations fall out of this family.
Mm-hmm.
Okay. Yeah. So you said the monogram is that the mark points are unipotent, and
yes. But so if you consider twisted version of this theory, which leads to Darbu equation, for example, in the case of 4 points, then they will not be unipotent anymore. They will be semi-simple with arbitrary eigenvalues in generic position.
We're also considering those things too. Okay.
Yeah, you can consider those things too, and there will be a parallel theory.
Good. Yeah. Unfortunately, we have to cut here. So thank you very much, Pavel, for a very clear talk. Yeah, I'd love to follow up on that. So let's thank Pavel. Then are there any other questions? No.
I just have a question about the holomorphic half.
Yes.
For me, so we can still consider the Hitchin system for the holomorphic half, where the wave function is a fraction of a line over bond G. And in that sense, wouldn't we be able to consider the Hecke operator there? So only for the half.
For holomorphic, I don't know how to define Hecke operators. So I don't know. So the eigenfunctions of, so the problem is the following. So eigenfunctions of the Hitchin system, which are holomorphic, they are not really functions. They are multi-valued. So they only live on the universal cover of band G, or rather of band G without there is some, they have singularities. So they're only holomorphic at points which are called very stable, which means that there is no nilpotent non-zero Higgs field. And so this set of very stable bundles is an open set which has a very big fundamental group, and so these functions live on a universal cover, so they change according to some representation of this fundamental group. And so the only way to get a function on band is to consider non-holomorphic function, which is a combination, which is Hermitian combination of the type of I showed.
I see. So the point is to make a function, not a multi-value.
Yeah. Yes, because you have to, okay, so if you have in analysis, you have L2, and so you have Eigen Functions, they are actual functions. I mean, they may have singularities, but they cannot be multi-valued. And so, but they are obtained by combining finitely many holomorphic functions, which are multi-valued with their complex conjugates in a way that you get a single valued combination. And there is actually a unique way to do so, because there is a theorem proved by Gates-Goria that this demodule is irreducible. The Hitchin demodule, quantum Hitchin demodule is irreducible. And so this means that there is only one way up to scaling to make this combination.
I just have another quick question. Why do we prefer PSO2 over SL2?
PGL2. Well, I mean, it's, I don't know. This is in some sense, the most convenient. There is, you can do also the SL2 case. The changes will be small, but it's there are small differences, and this case, the case when the group G is adjoint and the Langlands dual group is simply connected is the most convenient case for this type of theory.
Thank you.
Thank you very much. Yes, unfortunately, we have to stop it here. So thank you very much, Pavel. That was very nice. Yeah, so let's take a 3 minutes break, and then we'll begin at 6:20 with Junichi Shiraishi's talk. Junichi, are you ready to share screen?
I try.
Yeah. Yeah, we see the slide. Yes. Yeah, good. Yeah, we see your annotation. We can see your annotation as well. Okay, so let's begin at 6:20.
Can you hear me, by the way?
Yes, we can hear you.
Okay.
Okay, are you ready, Junichi?
Okay.
Okay, good. Great. So let's continue. Our next speaker is Junichi Shiraishi, and he will talk about quantization of discrete Painlev 6 equation and Shakirov's conjecture.
Okay. Thank you very much. So, anyway, what I want to talk about is some connection between Shakirov's conjecture with it can be said that it is connected with discrete Painlev equation, but in the quantized setting. So let us recall what Shamil wrote us. So first, we need this. So this kind of thing. So this is some particular version of necklace of partition function, or it can be thought about as the conformal block for some discretized version of the Virasoro algebra. So anyway, it is this kind. No, I will explain the notations here and later. But I guess everybody knows it. So
can you remind us the Z is the Eigen function of what? Of elliptic arrest, or
no, so Z is the partition function first.
Okay.
And what he does, he tries to restrict the parameters by some way. By some way, I think he's inserting degenerate fields. So it is this kind of 5-point conformal block. Yes, and he takes one to be something like phi1 2 or phi 2 1.
Yes, and it's for SU2, right?
Yeah. So then, before doing this, he wrote it as Z. So we have many parameters. It is not clear how to handle with them, but at least how many we can count. So it seems probably 9 first. Then he restricted like this. Phi 1. So what is V? V is Q1/2 T minus 1/2. The QT, so who are they? So they are associated with McDonald parameters. So why McDonald? Because it is a discrete version of the Virasoro with such parameter. Okay, so this V he uses is very nice, and I use it. So, and after such restriction, so we have one degenerate field inserted. This partition function becomes something very interesting. Very interesting means what? So in the ordinary conformal setting, we already know that such conformal block satisfies some differential equation. I mean, a BPZ equation. So that can be interpreted as the Painlev. I mean, Okamoto Hamiltonian acting on such thing. Of course, this Okamoto Hamiltonian is quantized version. So anyway, I expect the similar thing happening for the discrete QT version also. So I don't know if it is good to do it here or not, but so I use such notation for the infinite product. And no, I wrote it like this, but so this is double infinite product in the usual notation, but Shamil uses such and such notation. So using such notation, he immediately start writing an interesting equation before. So there is one thing which I have to explain. So he uses some operator gamma, so that is I am afraid that this is mine, but Q to the Laplacian operator. So because of such a definition, this gamma is not acting by a simple shift operator, but it is creating on the monomial, like x to the n, giving us this Q to the quadratic. No, it is easy to see that this gamma is acting on a series of x and also lambda over x. So this gamma operator is acting on the ring of former power series in x and lambda over x. Yes. And of course, we have some A1, A2, A3 like coefficients in between. So which Shamil gives explicitly like this. Let's see how A1 looks like. A1, here we have phi. Phi, it is just this infinite product, and this capital phi, that is double infinite product. So the A1, that is just the product with the infinite products. A2 also, A3 also, and inserting such here. So first, A3 is acting by multiplication by x or multiplication by lambda over x. Yes, so that is allowed on the space. So then you act by gamma. So then you continue acting by the similar structure A2. So then gamma. So then A1. So I don't know how he found this kind of equation, but he finally succeeded in doing this. The first thing which I wanted to try is to understand the structure of such equation in some, I don't know, better way. Better, I don't know. But one possibility is to make some gauge transformation. Gauge transformation, I mean, multiply some function to phi, so that will change the structure of this equation, surely. And I was searching such possibility to make this A1, A2, A3 bit simplified. So let us try to do this kind of transformation. By some reason, I take A3 doing this job and then 2 more phi's. So why A3? A3, I do not like this guy here. So I absorb this A3 in phi's. So then by some reason, I do not like these small phi factors in A2. For the moment, I cannot explain why, but let us try. I want them be eliminated. For that purpose, it is easy to have 2 phi factors applied here, just killing this. It's just easy to see. So let us do it. So then the result looks like this. So what is this? So phi, as I said, it is just infinite product. The infinite product here, 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 here. We have 4. So then some strange thing, gamma. So then phi, 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 then gamma. So then finally, we have such t shift in lambda here and some strange shift in x here. So no, such thing can be easily written by introducing a shift operator inserted here. So anyway, after some simple manipulation, we have some simple looking equation which is just equivalent to this original Shakirov. So how does it look like? So it looks like H acting on psi is just psi with eigenvalue 1. No, I do not know why the eigenvalue should be 1, but it is so. Now I checked this carefully, and I strongly believe that it is so. Of course, Shamil did such checking very much extensively, and which I could not reach yet. But anyway, I start from this equation to have something living nearby here. Nearby, I mean, so what I want to do. So I want to prove, at least, if it is possible, this kind of thing. But without any tool, it is very hard, it seems. So if we have some kind of symmetry which is compatible with this equation, so that should help us, surely. And actually, this kind of symmetry should be that Becklin transformation for Painlev 6. Yes, so in the discretized setting, so that is known that such thing should be the affine Y group of type D15. So let us try. Okay. No, just to have some notation. I start from the linking. So 0, 1, 2, 3, 4, 5. This is the enumeration. And we have such involution, and of course such involution. So altogether we have some group called the extended Y group. No, the simple reflection associated with simple roots are 0, 1 up to R5 generating the Y group. And extra thing like sigma 1, 0, 0, 1, sigma 4, 5, tau associated with such linking automorphisms making this Y group a little bigger. Bigger, something called extended Y group. Okay, so this is a starting point, and what I want, what people tried to use to understand the Painlev. どこか、これか。あ、そう。 So we need to use such multiplicative parameters AI. So that is nothing but the exponent of root, simple roots. And we consider such as a parameter for the Painlev equation. And they satisfy this multiplicative version of the while group reflection. Yes. And I also need the similar for linking automorphisms. So, as I said, Ri acting on Rj is just by this way. Sigma by that way. No, so sigma 0, 1. So they exchange the indices according to the way I explained and then make up such inverse. So that's all. And we need another variables called Fg. Why it is clear? Because Painlev equation is differential equation of second order. That can be written as a Hamiltonian system due to Okamoto. So we have a canonical pair of variables in this sense. And actually, we do it in a discrete version, but it is so. So we have F and G variables, and the while group is acting on F and G also as the Becklund transformations. And I'm just giving you the result to set up our notation. So how I is acting on F, for example, I0, 1, 4, 5, they act on Fg trivially, but the R2 is acting on F by rational way. So we have such simple rational factor multiplied to F. No, so that's all. So this is a rule. Then what do we know? So we know that these things are defined for each generators, and of course we need to extend such action, asking them to be ring homomorphism. So we have to be careful about the consistency to have the representation of the Y group acting on by this way. So that means we need to check the Coxeter relations. That is easy, really easy. So no, to do it by hand, it's not easy, but computer program can easily help us. So how we can write the Painlev equation by this setting? So we know that starting from the translation element of the extended Y group acting on the canonical variable Fg, so that is nothing but Painlev. To be able to say it a little precisely, I need this at least. So what is this? P, that is corresponding to the null root of D15. So usually it is written like Q, and people usually call it Q Painlev 6. No, so originally Jimbo Sakai initiated this kind of thing, and they used Q. But so if I do it, we have a very serious contradiction of notations. So we need to avoid it. And following Hasegawa-san's notation, I prefer to write it by P, not instead of Q. So I call it P discretize the P bundle to avoid any confusion. Anyway, so T acting on the element F and call it F bar. So it is very easy to calculate. So actually, iteration of the action can be easily traced, and then we arrive at such equation, which is originally found by Jinbo Sakai. No, just to make some comment, it should be reasonable. Here, so we have a very big symmetry behind such system, but at least we have to be careful about who are commuting with action of the translation. So we have several generators doing this. So in particular, R0, 1, 4, 5, they commute with T for sure. And something coming from the internal thing, 2, 3. So R2, R3, R2 multiplied by this way, that is also commuting with this T. And sigma, so sigma here, yes. So they commit. Tau, tau commit almost, but it fits the direction of the translation. Okay, so I think we have already finished recording the basic knowledge about, no, basic means almost zero, but commutative version of the discrete Painlev 6 equation. So, no, I forgot. So maybe this is important. So what we did our calculation starting from the simple roots alpha, having a multiplicative version of them. I mean AI, do the calculation. But the final result looks very complicated, and that things becomes unclear. So like here. I don't know why they appear by some, no, here. I cannot have any intuition. So after the calculation, it is so, but anyway. But originally, Jinbo Sakai, they had a very clear meaning of the parameters sitting here. And also Sakai later made a beautiful classification of such a discrete system using the geometry of curves, on which Cremona isometry is acting. Cremona, it is just birational, I think, transformations acting there, and we have a very interesting thing. And discrete Painlev 6 sits in somewhere in the middle of such classification. So as I was saying, it is better to introduce some notations like B, up from B1 up to B8. So because we are increasing the number of variables, we surely have some relations like this. B1, 2, 3, 4, 1, 5, 6, 7, 8, 1, 2, 7, 8, p squared, etc. So anyway, using such p parameters, Painlev looks like this, and actually this is the original form by Jinbo Sakai. Yes. So now we need to make a quantization of this program. No, I don't need it. So if I want to make any kind of calculation, I start from such table of action. Using such table, we end up with the result. Yes. So I want to do the same for quantized setting, and I just recall Hasegawa construction. Hasegawa first did this kind of quantization. So how he does? So of course, quantization means non-commutative or Q-commutative. We had the F and G, but now we have capital F and capital G. I just use Hasegawa notation, and so they are satisfying this Q commutation relation. Fg is Q inverse GF. No, just one comment. Hasegawa, he was using Q here, but I want Q inverse here sitting. No, nothing changed really, but the reason Q inverse here is just from the conventional notation for the quantum Virasoro story. I mean, McDonald Q. So this Q is McDonald Q. No, Shamil's Q. Yes. I cannot allow Q appearing here. So otherwise, we have big confusion. And accordingly, we need some slight modification of the Hasegawa construction because of the analyticity. Analyticity, I mean, we need to deal with some infinite product with parameter Q. Q and Q inverse, so they, if we exchange things, changes drastically. Yes. Small but important comment, probably. But so he introduces before. So what kind of space we have to have? So we are starting from A parameters, yes, and we allow them to appear as rational functions. So that's good. And we need the Fg also appearing as rational functions because it was so in the classical. So, but we are doing it in Q-commutative situation. So we have to be a bit careful about the making quotient. But it is known that such polynomial ring generated by Fg with such condition is already satisfying Ore condition, so we can make a skew field. So for the time being, we consider our things over such skew field, which is denoted by some. I forgot. So anyway. So then what to do? So I just make copy of the classical version here. Of course, with some careful treatment about the ordering. Ordering should be like this, but otherwise we don't see any difference. And we have Q appearing here by this way. So that means F is going to here, Q over F, or G to Q over G, something like that. Q parameter appears here only, and maybe here, but it is hidden. It is hidden because I demand the ordering be this. So anyway, this defines the action of Y group on such skew field. So we can make up some calculation. It is much tedious because of the careful treatment of the ordering. I do it, and then I could finish it. So I believe Hasegawa-san, and I believe such things working perfectly. Perfectly means that so such action extended by ring homomorphism way is generating some Y group action, namely Coxeter relations are satisfied. The checking of Coxeter relation is amusing, but today I don't have any time. Okay. At least it is written. So I want to check, for example, this. At first sight, it seems tedious, but at least it is rather strange for first, but it is so. To check the Coxeter relation, we need checking this three-term relation. But actually, we only need to three-term, two-term relations by some reasons. Anyway, we can do it. So it is not necessary, but I just want to show you the explicit way of action. To not just to recall the feeling, how it is going on. So take the translation and write it as a product of reflections, and then act it on F. Yes. For example, F first act by sigma 4(2) R3 R1, so it is just this, nothing changes, but starting from the action by 0(1), it getting this kind of change. I think it is correct, and continue. So then we arrive at the quantum Painlev equation in the sense of Hasegawa. Yes. No, it is good. We have this kind of non-commutative analogy, but Hasegawa wanted to have some understanding from the point of view of adjoint action. Adjoint action means F is going to this kind of F bar, but he wanted to write this as some operation like this. I mean, adjoint action by some strange looking operator. And he claimed that such operator exists. And this I really need to do.
Shiraishi-san, so,
Hi.
so you erased
Hi.
So H should be F, I guess.
H.
But yeah, no problem. Yeah. No, so you have already erased the.
I wanted to write something like this.
Yeah. Right.
Sorry. Thank you very much. So what he wanted to use. So of course we need to have some good control of such adjoint action by some mechanism, and there is no chance to have something other than Young-Baxter relation for sure. And it is the solution found by Patev Zamolodchikov. Of course, Patev Zamolodchikov first, but later Patev Volkov, many people continue to use this particular solution. Let us recall. So I want to have this notation for the theta function. I think it is kind of standard, and to make up such ratio, theta function sitting here, and making some z shift here, and put it on the denominator, and call it Rzx. So then, because of the Q commutativity f g q inverse gf, so we have this Young-Baxter equation. No, of course, we have this kind of dilogarithmic identity, or something like 5-time identity. No, we can compare such R operator with Patev Zamolodchikov by this way. This way means start from a very fundamental identity, which is due to Ramanujan for this hypergeometric bilateral series, one psi 1. Bilateral means this is just Laurent, and not the series extended in one direction, but it is extended to two directions. So no, so this kind of bilateral series can be factorized. This is what Ramanujan found. Just using this, we have such expression, which is found in this old literature by Patev Zamolodchikov or Patev Volkov. So anyway, it is very important object to this business. And maybe I do not have much time.
Yeah, there is 10 more minutes. 12 actually, 12 more minutes.
Okay. Maybe just one word. I agree that Hasegawa-san wants to write everything as adjoint. So that means the Y group action on the letters A. So that has been already defined, but this has to also be written as adjoint, and making it give us some simple exercise, but it can be done. And we have some adjoint way of writing such action. And the canonical variable side, the FG, so we need to use this Young-Baxter. So it is very amusing to make up such calculation. R inverse gives us F times some rational. So that is nothing but R2 acting on F. Yes. No, so far so good, and everything is fine. But we know that. So the translation is a product of R, but finally we need the sigma 01, sigma 45. So at least we need to be able to write this combination. We call it sigma according to Hasegawa. And we have here a big trouble. So how to do it? So it is not clear at all. And actually, Hasegawa-san made some calculation, ending up something different from what I showed today. That means there is some big freedom on choosing such adjoint representation. So such difference should be carefully studied because we are going to study some difference equation associated with such construction. For the time being, let us proceed as follows. The basic strategy should be the same. So no, we start from some theta function with argument, in this case, F inverse G, and make up such adjoint action on F and G. So it's very nice. It is giving us very simple action like this. And I do the similar with quadratic theta, acting on F, G by this way. So if I make up some, here, so we have some parameter Z, like the parameter in the R matrix. This Z has to be commutative. So we know that making up such a cubic combination of the theta, actually it is -3. Power is -3, but doesn't matter. Giving us this kind of very simple exchange of F and G. F, G, G, Q over F. So this kind of thing. So if we continue this kind of thing, we end up with something we want. Sigma, this combination is acting on Fg by this way. So if I continue applying the adjoint action twice, so we get it. So that means some adjoint action by theta to the 6 will do the job. So this is just what Hasegawa-san wanted to do with some other choice of the combination. And as I said, so we have some freedom of choosing such parameters. So I take this particular choice, A0, A1 here, A4, A5 here, by some reason, which I explain next. Now I start from this quantum Okamoto. The H is by definition R, then sigma. Yes, corresponding to the translation. Before showing the result, it's better to start gradually doing the calculation. So as I said, the H is R psi, so that means R operator together with small rho, so that is acting only on the parameters. So then that means R1, R0, they doesn't carry this big R satisfying Yang-Baxter. But R2 here, we need to insert this R. Yes, R3 here, R. So in total, we have 4 R operator, F, Zamolodchikov inserted. And in between, we have a small rho. They are acting on this small A parameters only. So we need to make up such shift end up with such combination R. Yes. So what should be this choice? Recall that R Z X, it has such theta function in the numerator. So I want this piece killing this theta function sitting in the numerator. So careful analysis, not easy analysis shows us that it is possible. Canceling such theta functions in the R, so we end up with this kind of thing. So this is this part comes from the first R operator. So because of the cancellation, we don't have anything here. And here it is so. But I should have been careful, but I had not properly done. So from the construction, we have to use G here, and F here, and we have 6 thetas sitting here. And I want to bring 3 of them inside. But when I do it, such middle setting F changes into G, like here. Yes. So anyway, that's all. What I need to do. So the result is this. So if I calculate Okamoto carefully, so then I arrive at this kind of operator. And as I was saying in the beginning of my talk, so Shamil was using some operator that is Q to the Laplace operator. Yes, and it is clear to see. So this theta with F inverse G as its argument playing the same role. So I mean, so this is acting as such operator up to scalar multiple. So this is just identical with the operator which Shamil wrote. Yes. So that means Shamil's equation is just Okamoto acting on somewhere, and it is giving us the eigenvalue problem. And this psi is just constructed by Nekrasov. So that is what he's saying. Yes. I think I have 3 minutes left.
Yeah, that's right.
Okay, so how I can try to proceed. So what I want to understand the symmetry, not only the action of the translation. Okamoto is fine, but I just want to study more carefully all of the action of extended while group. So to do that, I need to have a good control of Painlev parameters. I mean A0 to A5 or B1 to B8. So while group is acting there together with FG, of course, but at least A parameter or B parameter has to be controlled. And I also need to know why we need such. No, we need, but how we can actually study the action. No, it's better to have some coherent notation. Coherent notation looks like that. So starting from such a wave diagram, I associated parameters x, u, this way. And locally, so they satisfy the set of balancing conditions. So that is what we need to do for the topological vertex. Yes. And the result of topological vertex gives us a necklace of partition function by this way. Yes. And we know that some bunch of infinite product attached to this kind of thing because of the construction. So I call it G or Euler factor. And together with Euler factor, what I have. So we can make up some S-duality of the graph. So because it has been already proved by Fukuda, Okubo, and myself that so we have some S-duality satisfied by this kind of very big extension of the hypergeometric looking like series. So no 0 minutes, but maybe this is the final slide which I show. Let us start from the wave lattice with size 2, 3, yes, and arrange B parameters like this. B5 here, for example, B7 here, 6 here, B2 over B6 here, 1 over 6 here, 3 over 7 here, etc. And consider the necklace of partition function with such parameters associated. So now we are ready to act by the Y group on this quantity. Why? Because how we act by Y group on B parameters, it is just by this. Yes, it is immediate to make such action. In this G variable, it is not so simple, but when we study the action which keeps such G or which simply reflects G to Q over Z, we can study rather easily the action of such and what we can prove. So we can at least prove that so R0, R1, R4, R5, that was doing this. Yes. No. Total confusion. Now we have a 0 node, 2, second node, 4th node, 6th node. So we have such reflections. The reflections acting on this side. Minus 2 nodes. So I really needed to attach this kind of Euler factor. So there's no time to explain why, but so because we have the technology which is established by Fukuda, Okubo, myself. So that will give us this particular choice gives us the stability of the action, the psi function under the action of R0, 1, 4, 5, and no, I stop here. So as I said, the sigma operation is also acting on this psi. So by using mathematics, I can check that it is also stabilized in this psi. And as I was starting from, so Shamil's equation is written by the action by Okamoto H on psi, giving us the eigenvalue equation with eigenvalue 1. Okay, so far I wasn't able to finish things nicely, clearly, but at least we have such understanding. Okay, I stop. Thank you.
Thank you very much, Junichi. Yeah, it looks very impressive. Yeah. Are there any questions?
May I ask a question?
Mm-hmm.
So in Jimbo Nagoya Sakai's work on Q Painlev 6,
Okay.
they have 8 tau functions and 8 bilinear relations, right?
Yeah. Yes.
I wonder what are the generalizations of these 8 bilinear relations for quantum Q Painlev 6?
No, I think their situation is for classical. Classical, I mean commutative, and this situation is for non-commutative. By that reason, situation is a bit different. I mean, they are looking for some properties concerning tau functions, but here, no clear understanding about tau functions.
You mean for quantum Q Painlev 6, there is no tau functions?
No, this is quantum analog, so non-commutative. How we can introduce tau function? So that is already kind of problem, I think.
Okay. Thanks.
I have a question.
Thank you. Yeah, go ahead.
You construct the wave function psi, which is the eigen function of. So is this equation really, or is it somehow related to the QKZ equation?
No, good question. So probably so. No, take R2 for example. This Y group element R2 that is realized as a joint or direct application of such Patev Zamolodchikov times some very little simple object. So suppose we have some control of such operator acting on somewhere like psi. I don't know if it is satisfying this kind of eigenvalue. It will immediately gives us some contradiction with this. But suppose we have some kind of identity which is looking like that. So that means this R is acting on somewhere and something else that is some kind of differential operator on the parameters acting on the same. So this is nothing but kind of KZ equation. No, I think so.
Yeah, I think for SU2, right, should be almost 1-to-1, right? So like you have this defect equation for dimension 4, right? So it's with a sphere with 5 points.
Yeah, so anyway, so this kind of equation which Shamil wrote is really nice, but it is complicated at least. And it's better, as you are saying, to have a much fundamental thing. Fundamental like QKZ or KZ.
Well, I think then we should understand what's the geometric meaning of that R matrix. Can you remind that what is it like the?
No. So they were using this R matrix for quantum Eigen on a lattice or things like that. Yes. Mm-hmm. Or better to look at Hasegawa's paper, starting from solvable lattice setting, where we can start from the Young-Baxter or quantum group. The geometry or algebra structure should be very clear. Something unclear is the equation. So this kind of equation should be regarded as BPZ equation. But it doesn't look like BPZ.
Yeah, because we don't live on a torus, right?
No, nothing is clear to me. So anyway, we have to have some good understanding about all of this. So as I was saying, some operator like Q2 Laplacian plays some role. And it is very new, at least to me. I just want to understand how, why, what is the reason, what is the proper way of handling this situation. So all these are the problem.
Okay.
No, so just to compare. So Q to Euler. So that is just the shift operator acting on X. Tx is just Q shift. Yes. So every equation which we have studied carefully takes this for example, McDonald system. And some kind of extension of this idea, Peter, Shamil, they allow having infinite order and call it elliptic. So this is very close to this elliptic expression. So we have to, anyway, understand this better. Otherwise, nothing comes out of this construction, probably. Okay.
Okay, thanks. Are there other quick questions?
May I tell you some comments on the tau function? So actually, I can introduce tau function for the non-commutative setting, but so I can, but nearly I can, I should say. So it means I need to check some well-definedness of the plus or minus in some tedious way, and I'm lazy, so that's why I have not written down the formula or the equation for the tau function. Sorry.
You were saying that your situation is like that for many years, 4 or 5 years or more. I don't know.
Yeah, I'm sorry. So I tried to do that for higher rank case, but yes, so I'm just lazy.
No, let me try to understand what you said. So you have a way to define quantum tau functions, and you have equations. Yes.
Yes. So you just well, how to say, eliminate or just divide the equation into numerator and denominator. In a sense, yeah.
Yeah, just as in the ordinary set. Okay.
Yeah, yeah.
Okay. Good. Thank you.
Okay. So let's thank Junichi again. Well, with your virtual claps, right? Yeah, thank you. And then, we have last speaker, Wenbin. Are you ready? So maybe you can go like in.
Ready. Can you hear me?
Yeah, maybe you can take like 1 or 2 minutes break. Yes, so that folks can catch the break.
In the meantime,
you can share the screen.
right. I don't have. Now I see the option. Good. Can you see it?
Yes, we can see it. Tetrahedron instantons.
Great.
Yeah, let's continue at 7:20:25. Yeah, let's be back in 2 minutes.
So we will resume in 2 minutes.
Yes, in 2 minutes.
Okay, good.
I think it's March 9th in China, right?
Sorry, what?
It's March 9th at your place, right?
Right. Yeah, it's actually at noon, March 9th, but prefer to use local time.
We live by Berkeley time.
Yeah, I just prefer to use actually the local time. Well, by local, I mean your local, the workshop's local time.
Right. Yeah. So coincidentally, we have the same schedule as Aspen, but with Aspen, it's because of skiing. We have talks in the morning and in the evening. But because in afternoon folks go to ski, but now we have folks in different places. Right? So, yeah.
I mean, I know it's always a bit difficult to organize this global event. Yes, thanks for the invitation and all your work on organizing this.
For sure, it's really nothing. It's like, you know, send some emails with them. Okay, so let's get going. Our last speaker is Wenbin from Tsinghua University in Beijing, and he will tell us about tetrahedron instantons.
Hi, everybody. It's my great pleasure to give a talk in this elliptical integrable model workshop. I think if you look at my title, my topic might be slightly off from the main theme of the workshop, but I hope during my talk you will see the connection between elliptical and integrable systems. And in the end, I hope I can try to convince you that there is certainly some interesting possibilities that connect the instanton, especially the tetrahedron instantons with the elliptical integrable system. Okay, so this is works with my collaborator Ali Pomoni and Xingyu Zhang. One of the one paper we already published last year, and the other half of the talk is based on the work we are currently working on. So for the plan of the talk, first I will have a brief motivations about our work. So we basically would like to generalize the usual Yang-Mills instantons and through the brane configurations and study its modular spaces. And we use certain tools, especially instanton partition functions, to study the modular spaces of these new instantons. And I found that it provides non-trivial test of the M series and type 2A duality. So after the motivation, I will explain in detail what in fact is a tetrahedron instanton, how are they constructed in string theory, and I will also give some examples of such instanton modular space explicitly. Then I will show the computation of this some invariants on the instanton modular space, in particular the instanton partition function. And in the last part, I will briefly mentioning the work in progress that we try to match the instanton partition function and the index of M series. Okay, so let me just start by briefly review the usual Yang-Mills instantons. If we look at the Euclidean action of 4D Yang-Mills series, which is just this simple term. And this action can be written as a complete square plus a topological term. This is a usual Bogomolny trick. And so besides the usual perturbative vacuum of the series, because of it can be written as a square plus a topological term, one can find the other non-trivial minima of the action with a finite action, which are called the instanton or anti-instanton solution, which is just they have to satisfy the self-dual or anti-self-dual Yang-Mills equation. This F tilde is the hot dual of the curvature F, and the topological term. This topological term is always an integer, which is called instanton number. Okay. For example, if we consider the gauge group to be as simple as U2, and sorry, and consider the one instanton example, you can actually write down in certain gauge that the connection explicitly as this. And this instanton solution is characterized by 8 free real parameters, that is 4 complex parameters, which are the position of the instanton and the size and the global SU2 gauge rotations. In general, the space of instanton solutions up to local gauge transformations is a smooth manifold. And we denote this modular space of instantons as mg, k. So they are determined by basically by the gauge group and the instanton number. Then, although this modular space of instantons are the modular space of some partial differential equation like the self-Yang-Mills equation, so there is an algebraic way of describing this instanton modular space, which is called originated by ADHM. So it's called ADHM construction. So if we are talking about SUN instantons with instanton number k, if we want to get the modular space, we can start it from this following ADHM data. It contains 2 k by k complex matrices, 1 k by n complex matrices I, and the other one n by k complex matrices J, and the following 2 moment maps. Okay, the following 2 moment maps, and then the UK gauge symmetry act on this matrices like as following. Then ADHM found that the instanton modular space is isomorphic to the space of all these matrices satisfy this constraint and up to the UK gauge transformation. This is a nice algebraic way of describing the modular space, but it has a problem that it's a non-compact. So it's non-compact due to small instantons. Then to avoid this non-compactness, Nakajima introduced a smooth manifold, which can be obtained from Uhlenbeck compactification of this original instanton modular space by just resolving the singularity. Basically, you instead of this the real moment map equals to 0, you set you consider the slice where the real moment map equals to some positive number times the identity matrix. And this M tilde is now become compact. Okay. Now there is also a nice string theory picture of this modular space. If you consider this Yang-Mills instanton, you can view this as just KDP brains probing the stack of n coincident DP+4 brains in type 2A string theory. Okay, for here I use the lines to show to represent the DP brain and planes to represent the P+4 brain, and then you can consider the strings connecting this different brains, and if you sort of leave on this higher dimensional brains, the effective theory is sort of a Yang-Mills theory. So then this lower dimension brains can be viewed as some instanton solution of from the point of view of the effective theory on the P+4 brain. However, you can also use the viewpoint of effective take the viewpoint of an effective series on this lower dimensional brane, and then the same configuration can be described, especially the modular space of instantons can be described by the Higgs branch of this the supersymmetric gauge theory live on the lower dimensional branes. Okay, so to get the even more, to get the compactified ones, Nekrasov and Schwarz just put this brane system on a different background. Okay, and then in string theory, you also have to turn on a non-zero constant background B field to make the supersymmetry work. So yeah, the punchline is that there is a nice geometric picture of different branes of brane system of different dimensions to describe the instanton the instanton configuration. Okay. And Nekrasov also introduced invariance, which we call instanton partition function, on the to better study. It describes the modular space of instantons. It's roughly speaking, so this partition function Z is a sum over a graded sum over partition functions for different instanton number K, and for the each Z partition function for a particular instanton number is sort of the integral over the compactified instanton modular space with some equivalent parameter. So the equivalent group is the maximal torus of the U1 square cross UN. This UN from the instanton is from the higher dimensional branes, and this U1 square is from the omega deformation. If you try to make this compactification. Okay, this Nekrasov instanton partition function is a non-perturbative part of the supersymmetric partition function of a 4D n equals to 2 series. Or if you're considering a higher dimensional counterpart of this instantons, it's a higher dimensional series in the omega background. Okay, so this partition function can be evaluated exactly using localization techniques. And the result can be expressed as a statistical sum over a collection of random partitions, which I will show you later. So so one good thing about this localization is you can compute this partition function in the gauge theory side, or you can just use another viewpoint, the viewpoint of lower dimension brane. Compute this as the partition function of certain lower as partition function of supersymmetric index of the supersymmetric series leaves on the lower dimensional branes, which simplify the computation greatly. Okay. So this Nekrasov partition function has a connection with a lot of different area of math and physics. For example, it connects to Versora and W algebra conformal blocks. It also related to cyber-Witten theory and refined topological strings on the Pahlavi-Yau-3, and also digraph Wafa matrix models, topological strings on Riemann surface. And especially through the work of Nekrasov and Shatashvili, the partition function is related to the quantum integrable systems. Okay, good. Now I mentioned integrable systems, and I only need to mention elliptic, then I'm done. So before I proceed, any questions so far in the audience? Okay. If not, let me start with our setup, our tetrahedron instanton setup. So we are trying to study. Remember previously we say that this instanton, Yang-Mills instanton can be viewed as some dp branes plus together with dp plus 4 brane system. So we're trying to generalize this picture to more complicated brane systems. So here we would like to study the D0, D6 brane system, where we use these D0 branes to probe in a configuration of intersecting D6 branes. So remember recall that in usual Yang-Mills setup, all this D4 branes, D higher dimensional branes are stacked together. But now we allow this higher dimensional branes to be occupied in the different direction in the space time. For example, if we start with a 10-dimensional space-time, and we call this time as we compactify the time x0 direction into a time circle, and then we call this x1. We group all the other. We group this x1 to x8 direction into 4 complex directions, C1 to C4. And leave this x9 directions. Then we would like to consider let the D0 brane occupy the time direction, and then the D6 brane. Notice that each D6 branes have 6 space dimensions. So each 6 brane, they occupy 3 out of these 4 complex directions. Okay, for example, and we denote we label the 1, 2, 3. We label the direction, complex direction that this brane occupies. So 1, 2, 3 means that this D6 branes are supported on the C1, C2, C3 together with a time circle, and then 2, 3, 4 means that these branes. This brane occupies or supported on the C2, C3, C4 directions. Okay, so we have 4 different choices of D6 branes, which are intersecting with each other, and none of this D0 and D6 branes occupy the X9 brane. So you can also make a T-duality. Since this is type 2A picture, you can also make a T-duality on the X9 direction to make every branch from D0, D6 system to a D7, D1, D7 system. Right. I mean, by then T-duality tells us that these two configurations are related. Okay. So to better keeping track of all these things, so we draw a tetrahedron here, and each node here represents one of the complex direction. Therefore, the face, each face, since it has 3 vertices, each face represents one stack of one type of the D6 branes. Okay, so we use the label 4 underline as to denote the set of 1, 2, 3, and we use this 4 underline plus a check denotes the set of all the faces. And since we use this tetrahedron to encode the different type of D6 branes, so we call this D0 D6 brane system the tetrahedron instanton. Okay, because it's a generalization of the Yang-Mills instanton as a brane system, and it also can be nicely encoded in a tetrahedron. Okay, and Any questions on the on this particular on the brain setup? Okay. So I would like to mention one more thing is that if you randomly write down all these configurations, usually you don't preserve supersymmetry. And for physicists, we like supersymmetry because with supersymmetry, the quantum corrections have good control. So in order to preserve supersymmetry, you need to turn on the B field here, background B field. And in general, the B field in this setup, B field can be written like this, and we just and the field strength of the coefficient is a sort of parameters in our theory, and these parameters cannot be arbitrary value. You actually have they have to be very particular, certain particular value to restore the supersymmetry.
So how many superchargers are preserved in most generic case? Well, when all these sixes are present, 2.
So in general, you have no in general you have no superchargers if you take just very generic B field. But if we found that if you take this particular combination, you have 2 supercharges.
Okay, yeah, but basically the same kind of setup as in Nekrasov. So
yes,
you have 0-2 symmetry, but you have 3-dimensional.
Right. It's very similar to the Nekrasov's magnificent 4 model, and actually I will show you that they are connected
by some duality, I guess. Yeah.
Right. So so actually, I would like to say that view our model as some Hecke condensation of the magnificent 4 model, and you will see some evidence for that. Okay.
Yeah, thanks.
Okay, no problem. And when we found that the supersymmetry is restored when you consider this parameter, and in this case, if we look at the effective theory on the D0 brains, the superpotential can be viewed this way. And this B's and I's you can view them as complex matrices. They are from B's are from D0 strings, and I's are from D6 strings. Okay. And in order to obtain an analog of this compactified modular space, we also need to take R greater than 0. Okay. So in the end, the low energy effective theory on the KD0 brains can be described by a supersymmetric gauge matrix model with which gauge group UK, and it preserves 2 supercharges. Also, if you make T duality on the last direction and making it a D1, D7 system, the low energy effective theory on the lower dimensional brains can be described by a 0,2 supersymmetric model. Okay. And then you can also visualizing this low energy or summarizing this low energy supersymmetric gauge theory on the D0 brains by this quiver diagram. It's a generalization of remember that when Nakajima talked about his until he also had a quiver like this. Roughly. Right, so he had a one node, and then there's a frame node representing the ND P plus 4 brain, and then there are 2 self-connecting lines. So so this is Nakajima's quiver, and here to get to describe our tetrahedron instantons, you need 4 different framed nodes representing the 4 different type of the D6 spring, and this central nodes represent coming from the D0 brane, and this B field, this sorry, not B field, but this pyramid matrices B, different B's they coming from the D0 branes connecting the D0 D0 strings connecting the D0 branes, and these lines connecting the central circle nodes to the frame nodes. These are the I matrices. These lines represents I matrices in the series. Okay. So you can see that our quiver is a generalization of the quiver that Nakajima considered, and the modular space of the tetrahedron instantons are defined also as the Higgs branch of this quiver gauge theory. Okay, now with the superpotential, no, sorry, this is not superpotential. This is the actual scalar potential. With the scalar potential, the modular space is just the vacuum or the minima of this scalar potential, and we can solve this solve the equation and find the minima of the potential, scalar potential, or the modular space of tetrahedron instantons as described by the following way. Okay, again, we have it's very similar to ADHM construction. So we have B fields, but we have 4 B fields or B matrices, and we also have 4 I matrices. They have to but now we have we actually have 3 moment maps instead of 2 in the Yang-Mills case. So the real set of the real moment map is again very similar to the previous Yang-Mills case. And the complex one can be viewed as the commutator of B and B matrices. There is an extra set of moment map which relates to, which are the product of a B and I and corresponding I matrices. Okay, and the gauge group, the UK gauge group, acts on the matrices as the following, and the whole modular space can be viewed as a slice, which is defined by this moment map up to the gauge transformation. Okay. So this looks this is a generalization of this usual ADHM instanton modular space, but it still looks complicated. So let me give you some example and show the connection between this tetrahedron instanton modular space and other familiar ones. So if we take the n vector as 1, 0, 0, 0, which means we consider only one D6 spring, and no intersecting D6 springs. Then in this simplest case, the tetrahedron instanton modular space reduces to the modular space of certain torsion-free shapes on C3, which are already studied by people before. And if we again look at the instanton partition function, but this time instead of we drop the condition we drop this restriction that theta equals to 0. So if we remove this part from the definition of the modular space, you see this modular space becomes exactly the modular space of the magnificent 4 model studied by Nekrasov and the collaborators. Okay, so this is sort of a certain apparent connection with magnificent 4 models. And okay, any questions? Okay, let me give you some examples, some explicit description for the instanton modular space with k equals to 1. So so if we have only one instanton number is 1, and let's take the all the d6, the situation where all the d6 branes are parallel with each other and no perpendicular branes. And then if you look at the then apparently there is no this so the I matrix corresponding to all the other directions, they have to be 0. And if you look at the let's go back to the sigma condition is a b times corresponding I. If this i's are b times sigma has to be 0, and sigma is b times I. And if this I is already 0, then that means their corresponding B1, B2, B3, they are unconstrained complex numbers. These are complex numbers because we are talking about only the one instanton situation. So these are 1-by-1 complex matrices, which are numbers. And the equations in this case, there's no constraints on the B1, B2, B3, and the equation they have to satisfy just here. You can immediately see that in this case the modular space is just C3 times Cpn minus 1. Okay, if you together with this n parallel d6 branes, let's introduce m perpendicular the d6 brane which occupies 1, 2, 4 direction. Now we say, okay, this B1, B2 are still unconstrained complex numbers, but this time this B3 and B4 has to satisfy certain relation. So then depends on whether you take this I124 or I123 is 0 or not. The modular space have the following can be written as the union of the following pieces. So or in other words, it's in this case in other words, this instanton modular space has a stratification, and in this case, the first strata is C2 cross C star cross Cpn minus 1, and then this is the second strata, and this is the third one. So in general, the modular space of tetrahedron instantons can always have this type of stratification similar to this, but much more complicated.
You said the virtual dimension is generically 0?
Right. The virtual dimension is always 0. Yes. Because it's just you can compute it by looking at the components of matrices minus constraints minus a gauge. It's always 0. Yes.
And you show explicit examples with finite dimensional?
No, these are virtual dimensions. So so if you right, so the virtual dimension is very different from the sorry, it's different from the real manifold here. You were asking why in this case it's actually because for example in all this in the more complicated case these are the stratification, right? I mean it's a union of different smooth manifolds, so it really doesn't make sense to talk about its real dimension, right? But I guess you probably want to ask that why in this case when the thing is a manifold, it has an actual dimension, right? And the virtual dimension is still 0. Oh, okay. I'm not sure. Right. Sorry. Right. Sorry.
Look at the partition function, then there will be numerators and denominators, I guess, right?
Yes.
You always match the,
yes.
not the math.
Yes.
Yeah, unless there's any, some degenerate conditions, it's always, balanced out, right? It always should be 0. I think.
Yeah, I will see that when I see the partition function. Thanks.
Right. Well, I'm not sure I'm going to show the actual form of a partition function, but yes, indeed, if you look at the computation of partition function, it's always have a same term in the numerator and denominator. Right. Okay. Right. Okay. Now let me talk about instanton partition function, and we simply define the K-theoretical instanton partition function as similar to before, as this graded sum between the partition function of different instant numbers, and each piece is a trace over the Hilbert space of the word volume theory with K D0 instantons, and all this Q and T fugacity. So the Q fugacity labels the generator of this U1 rotation, and this T fugacity labels the Cardan generator of the symmetry group UNA. And so this is simply the definition of this instanton partition function in terms of the low energy effective theory. And to really compute it, before giving you the explicit formula, let me just deviate from the slightly from the what I'm talking so far. So up to now, we treat all these D6 branes on equal footing, but we can also choose the physical spacetime to be a certain preferred direction of this C3, say C3 1 2 3. That is, we call this D6 1 2 3 branes are actually physical branes, and then it will give rise to instantons on the C3, while the remaining D6 branes looks like codimension 2 defects in this D6 physical branes. And then one can also interpret the partition function as some expectation value of certain defects. Okay. So I would like also mention that if you make T duality on the X9 direction, there is also an elliptic version of all these instanton partition functions, where you simply replacing the different components by the theta functions. And okay, now I also connected with elliptic. So yeah, well. So now let me show you the explicit way of computing the form of the instanton partition functions. So basically, you just look at you start with the the effective theory on the lower dimensional branes, and write down the contributions. View this as a supersymmetric quantum mechanics, and write down the term correspond to the D0, piece and D0, strings, and then D0, D6 strings. So for example, this term, roughly speaking, this this term comes from the D0 strings, and then this term comes from the this term comes from the sorry, the D0, D6 strings, and since we're talking about D0, D6 strings, so all this these are just a product of rational functions, and if you would like to discuss D1, D7 system, okay, you can simply replace here by certain theta functions, okay. And you can see that indeed the numerator from the contribution from numerator and denominator from each strings, indeed they cancel, the number of terms are equal. And after you write down this this term, you have to perform a control integral, which are evaluated using the Jeffrey-Kirwan residue prescription. And the poles are labeled by a collection of plane partitions. The plane partitions which is a generalization of the usual partitions, and can be represented by certain boxes in the 3 dimension. Okay. So I'm not going to show you details about how to really find the poles, but it's a tedious and but procedural computation of the instanton partition function. Okay. However, we found that although so what you really need to do is just giving a particular configuration of this D6 spring systems N1, N2, N3, and N4, and then start with one instanton. You work out Zk, and then for 2 instanton you do the same computation and you continue on. And then the final instanton are just the greatest sum of all this. However, this looks hopelessly complicated, or at least very tedious. However, we found that the result of the full instanton partition function can be summarized in terms of a very simple plastic expression. So, although each term, each zk is a complicated integral of on the previous page, we conjecture that if you perform sum over all the instantons, the result looks just as like a simple expression of this. So here, this x bracket is just x to the half minus x to the minus half. And then we use the usual plastic exponential, where PEF is just the exponential of this complicated form. But then this the argument in the PE is a certain sort of a single letter partition function or a single letter free energy, where we define, we call it by this F. It's a very simple expression compared to the previous expression for the each instanton partition function. Okay, I have to say that this is this simple expression for the full instanton partition function is not a proof. It's just we just conjecture this form, we use computers to check it up to very high order of instanton number, and we also try different type of of the DC experience systems. So far, this simple expression worked very well, and but of course it's very nice to eventually give a proof of this particular result.
Excuse me, question. Can you represent the right-hand side as an infinite product, so that on the right-hand side you have just infinite products, no any summations?
The right hand. You want to write the right-hand side as
a kind of ratio of some gamma functions, Q gamma functions.
Yes, you can. You see, so each piece is sort of this coming from this X. Mm-hmm. And you can it's sort of because of the number of these terms are in the numerator and denominator are the same. It really makes no difference if you replace this X bracket as a 1 minus X.
I see.
And then
so essentially you conjecture some explicit summation formula of hypergeometric type in a sense.
Right. So I can if you plug in this explicitly, I can just write use the definition of PE to write this as a certain product.
Mm-hmm. Okay, thank you.
Product. Yes, it's just too complicated. I didn't bother to write it down. But yes, you can.
It's a gamma function with three. I mean, the elliptic gamma function has P and Q, and this is right. Like three parameter version of it. I mean, it's not a big question. I was just wondering.
It looks like a 4 basis, so it's kind of gamma 4. I mean, this more.
It looks like we have Q1, 2, 3, 4, but because these Qs are related to the new parameter that I mentioned before. So because of supersymmetric condition, we have to impose a constraint that all these 4 Qs the product of Qs equal to 1. So there are only the free parameters are Q1, Q2, Q3. So it's sort of the 3 parameter generalization of the gamma function. But
what about the convergence?
That's a very good question. Sorry, we treat this as a formal
power series.
All this formal power series, and we just assume that all this we assume the abstract absolute value of each Q are smaller than 1, and assume that we don't have any problem of convergence.
Okay, it's okay. Just to see the expression is very good.
Okay, good. Thanks for the question. And I think there is definitely a way to write it as infinite product, but I just didn't think about that in that direction. Right. Thanks for pointing out this thing. So this is a generalization of the plasticity expression for the Donaldson-Thomas invariants. And okay. So if you also let's go back to Peter's question about relation with tetrahedral instanton. So you see, if you look at Nekrasov results, they also for this a magnificent 4 models. Sorry, it should be Nekrasov magnificent 4 models. So they study the system of D0 branes with probing some D8 branes and anti-D8 branes. And their instanton partition function they also have this very similar plastic exponential expression, where instead of our Q here, they replace by mu. Oh, sorry, I forgot to mention that our capital Q here is a collection of this Q1 to the power N1, Q2 to the power N2. Is so remember that our 66 spring configuration was completely encoded in terms of this N1, N2, N3, N4, right? So this small n are denoting the number of D6 springs of each type. So you see this this information about this D6 spring enter collectively in terms of this Q. So this capital Q is the only place where these n's are this n's enter, and by definition, you see the partition function is symmetric when you under the permutation of this automatically symmetric under permutation of n's. That is sort of consistent with the fact that you know this different D6 springs are really on equal footing in our setup. Okay, but so in Microsoft's Magnificent 4 model, he just introduced this particular parameter mu to cap as a parameter for the mu is a relative position of this D8 brane and anti D8 brane. So our tetrahedral instanton partition function is just the Magnificent 4 partition function with the following substitution. You just replace mu with by the QA to the power n. Okay, so this is the indication that our tetrahedron instanton is annihilation of the D8 and the anti-D8 brane in Microsoft's model. But it just when the D8 and anti-D8 brane annihilate, it leaves behind a system of D6 branes, and described by this particular choice of specification of this mu parameter.
I have a question. So we don't have something like Coulomb parameters here.
It depends on the point of view. If you look at this, if you're looking at this from the effective theory of low energy, low dimensional brane, no, we don't have any Coulomb parameters.
D6 brane.
Sorry.
In the point of view of the D6 brane?
No, in the theory of D0 brane, none of these are viewed as Coulomb parameters.
Yeah, I was asking about so in the usual four-dimensional Nekrasov function, we have those Coulomb parameters, and those are Coulomb parameters of the fluid theory. So I'm asking whether we don't have it.
That's also a very, very good question. Let me see. Okay, so
P is the instant counting parameter, and Q1, Q2, Q3 are.
Yeah, these Q parameters are generalization of the epsilon1 and epsilon2.
And we don't have anything else.
So no, there's nothing left. Okay. Right. The previously, when you try to compute this, there are sorry. Right. The Coulomb parameters they are gone after you integral. You take.
In your Krieger picture, we have some symmetry groups, right? Like we have n1 to 3, n to 1 to 4, n to 3, 4. We have the symmetry groups for those nodes, right?
Right. This T is
We can turn on the equivariant parameters for those symmetries.
right. You can turn on this.
What is T? So
These T's are the equivariant parameters labeling the cardon of the UK the UNIA, right?
and then in your final formula or in the statistic exponential formula, where do I see T?
Wait. 1 second. Let me double check how this works. Can I just proceed and let's go back to.
In fact, so do you need like 5-10 minutes? Of like, how much time do you need?
To complete everything? How much time do I have?
Technically, it's already 55 minutes, but yes, like 5-7 minutes. Is that enough or not? Or do you need 10? Yeah, let's go for 10 minutes. Yeah, is that okay?
Yeah. Let me finish this first, and then come back.
Yeah, I mean, we have discussion. It's nice. Yeah, let's keep going, but yeah, let's not extend it for too long. Yeah.
Okay. Yeah, I understand. Right. So there's one more property. Except this simple final formula for the full partition function. It also has a decomposition property. While this the single letter ones, even for the N0000 ones, they can be written as the sum of the 10000 ones with just a different combination of the arguments. So you see this also for the arbitrary configuration, it can also be written as a sum of the 1000 or 0100. So we call this a decomposition property, and this looks like that each single letter seeds of the partition function has the structure of the orbifold partition function, where when you compute the partition function on an orbifold, it looks like the partition function without orbifold, but the sum of partition function without orbifold, but just with some twist, right?
Okay, you would orbifold some transversal planes, right? Like with independent discrete group parameter, right?
Right. We would like to interpret this property as that, and that is very crucial when we try to match with M series index. Okay, I will skip this. Just to briefly mention that all this partition function can also has a free field realization as some correlators in the free field theory. Okay, now I would like to use this. We would like to use this partition function as a tool to test the M series and type 2A duality. So we know that the M series, the type 2A string can be viewed as a weak coupling limit of M series, and then in the low energy limit, one is described by the 11-dimensional supergravity. The other one is 10-dimensional, described by 10-dimensional 2A supergravity, and also D0 brane, D6 branes. They all have the M series counterpart, which is a KK graviton and KK monopole. So a bound state of D6 and D0 branes on S1 can be lifted to the 11-dimensional bound state of KK gravitons in certain background. And this previously structure of a structure in the previous decomposition property, we would like to view this as this different K we would like to view as a certain orbifold of this this thing with just a different discrete group. And because of this, if the type 2A and M series duality is true, then this M series parameters, M series index should be the same as our instanton partition functions. Okay. But we to really get a match, because they are labeled by different parameters. To really get a match, we need to find a certain a suitable change of variables to really match the these two quantities. Just like this, when people try to match Donaldson-Thomas invariants and Guha-Kumar-Vafa invariants, you need a complicated change of variables. So, for example, it's again, if we consider the basic example where the D6 brains are 0, 1, 0, 0, 0, and the M series side is described by the plasticity. The M series index is a plasticity exponential of this simple term, and the partition function is described by this. Okay, so the dictionary is written here. So if you write down if you substitute the M series parameters by this one, you recover the you can recover the non-perturbative part from the instanton partition function plus a certain perturbative part. And using the decomposition property, we can also find the correspondence for generic n. For example, if you replace this, you replace 1 with n, and because of the decomposition property, you can interpret this as an orbifold. So here you simply change this C5 to some Zn orbifold. Okay, and of course you can do it for more generic case with n and m and more complicated ones. Then you have to change the M series side from simple C5 geometry to more complicated orbifold, and also possibly you need some resolution. Okay. So just to summarize what we did, we introduced the tetrahedron instantons, which are realized by the string in string theory by D0 brains probing some intersecting D6 brains, and we use the instanton partition function to capture compute the instanton partition function as to study the modular space of this instantons, and we try to use this instanton partition function as a tool to test the type 2A and M series in correspondence in a very generic brain setup. Okay, and of course we can extend our direction to several directions. One is we generalize the spacetime. We might try to generalize the spacetime from the flat one to some more complicated Calabi-Yau-4 manifold. Or we can also add in D2 and D4 brains in the type 2A picture, corresponds to the M series. Then this in the M series side, it will receive contributions from M brains. And moreover, so what we call tetrahedron instanton is just a certain system of brain. It's a brain system. We don't have a so far it's like we have the modular space, but we actually don't have the don't have the actual object. It's just some Brane system. We don't have the precise mathematical object behind this. Not like in the Yang-Mills instantons, you say, okay, it's a solution space of the self-due Yang-Mills equation. Or in some other cases, you can say this is a modular space of certain sheaves. So it also it is also very nice if in the future we could mathematically understand what are this mathematical model for this Brane systems. Also, one possible direction we would like to do, which might relate it to the theme of this workshop, is one could try to find the possible action of cohomological Hall algebra on the modular space of the
it's probably should be a bigger algebra or different algebra, right? That acts sort of naturally on the space of representations of that quiver.
Right. Maybe it's some generalization of this this algebra. I'm not sure, but I just it's a possible direction.
So it's like, you know, it's a like major question, like what is the most general algebra that you can find, right? So is there anything beyond Koha? And then it looks like your quiver looks more complicated, so maybe there is something beyond that, but it's still not clear. Yeah, so
not clear, right? So it's I just say it might be related. It's I got the inspiration from this work of these people, and also previous work by Galto et al. So they studied this Koha action on the modular space of spiked incidents, which are sort of three different intersecting branes on C2 and described by this quiver. So they found there is a Koha action on the modular space. And the nice thing is they identify this Koha action by with certain quantum group, and they also find there is a free field realization of this action. So that inspired me to think in certain ways. So our quiver is of course it's sort of generalization of their thing. I think you're right that we could try to find some action of the modular space of our tetrahedron instantons. It might be more complicated than Koha. I think there is such thing, and the result that the fact that there is a free field representation for our particular function somehow make me feel more confident that that such action might exist.
Mm-hmm.
So right, that's all I have to say. Thank you very much.
Thank you very much, Wenbin. Yeah, thanks for your talk. Questions? Oh, we did have some questions during the talk. Yeah, so I would like to ask all the speakers to email me their slides so I can put them on the website, and then once the video is processed, I'll upload it on YouTube so you can all have access. Great, thanks a lot. So, and I'll see everybody tomorrow morning Berkeley time for the second day.
Okay.
Thank you guys. Bye. Have a good night. Well, or good morning. Bye.
Whatever. I mean, have a
whatever day of the time of the day.
Okay. Thank you,
Bye,
guys.
everybody.